Hola, buenos días. Nosotros vamos a empezar cuando tenemos 20 espectadores. 20 espectadores. ¿Ustedes pueden me comprender? ¿Quién puede me comprender? Yo comprendo yo mismo. Okay, I'm gonna start. No one wants to interact with me in Spanish. Fine. ¿Tú comprendes tú mismo? All right. Empezamos. Okay. I'm just reading all your responses. I was, because I'm taking a Spanish 1 class, second period. So I had Spanish 1 this morning. And I participate just like I'm a student. Like, I don't even know if they know I'm a student. And I got put into a breakout room with this girl who was like the one who always answers the questions, you know? And I said, oh, it was like, oh, tú eres muy inteligente. You know, because she answers all the questions. I was like, you're very smart. And ella no me comprende. No, ella no me comprende. Uh, so then I revised my opinion and I said, maybe she's no es muy inteligente. Okay, I guess I'll start. Empezamos. Okay. So today we are going to talk about something called momentum. So we're done with energy for the time being. Okay, we're going to come back to it later on, but for now we're moving on from energy. There's a new quantity. It's called momentum. Momentum is denoted by a lowercase p, whereas power is typically an uppercase p. So momentum is mass times velocity. That's the formula for momentum, an object's mass times its velocity. It's a really easy way to remember the formula for momentum is to just flip the equality and write it as mv equals p. Okay. So does anyone know what MVP stands for? ¿Qué quiere decir MVP? ¿Qué quiere decir? Who knows what MVP stands for? I'll keep going. The units of momentum. Oh, some people wrote most valuable player. That's not right. In this class, MVP stands for most valuable physicists. And right now, for me, you all are the most valuable physicists. Okay, so I just wanted to tell you that. Okay, units of momentum. Can you tell I'm distracted today? I'm just like, I can't focus at all today. Well, I can focus, but I just can't focus on this right now. I'm struggling. Mass times velocity would be kilograms, are the units of mass, times meters per second. So the units of momentum are kilogram meters per second. So this is the momentum of a single thing. If you have multiple things, the total momentum is going to be P1 plus P2 plus P3 plus however many momentums there are. Okay? So that is called the total momentum of the system. You just add together the momenta. Tu debes venir aquí. Okay. Let's just do a little comparison and contrast between kinetic energy and momentum. Okay. So kinetic energy is in a lot of ways sort of similar to momentum because they both depend on mass and velocity. Okay, mass, velocity, but it's a different formula. If we look at the formula for kinetic energy, it has velocity squared. So what that means is if you're going to the left and you have a velocity of, say, -5 meters per second, when you calculate the kinetic energy, that negative goes away. So kinetic energy, if you're going to the left or to the right, you have the same kinetic energy. So kinetic energy does not depend on direction. Okay, so a quantity that does not depend on direction, does not have a direction, is called a scalar. Okay, so there are lots of scalars in physics. So for example, mass is a scalar. Your mass doesn't depend on the direction you're traveling in. Okay, you just have a mass. Another good example is temperature. Temperature, it's just the value for the temperature. However, if we look at momentum, momentum does not have v squared, it just has v. So if you're going to the right and you have a velocity of +5 meters per second, you have a positive momentum okay? But if you are going to the left and you have a velocity of negative 5 meters per second, you have a negative momentum. So the direction you're traveling in changes the value of the momentum, okay? So momentum does depend on direction. And so any quantity that depends on direction is called a vector. Okay? So energy, for example, is a scalar. Velocity is a vector because velocity is speed with direction. Acceleration is a vector because you can accelerate to the right, or you can accelerate downward, or you can accelerate upward. You can accelerate in all different directions. Okay. So why is momentum useful? Okay. Why is momentum useful? Well, I'm going to tell you why right now. Whenever two or more objects collide, so whenever two or more objects collide, you should think of momentum. So whenever two things are colliding, your brain should automatically think, okay, I'm going to be using momentum. All right? Because the thing about physics is there are a lot of different scenarios we can analyze. And because of the way this class is being taught, I will say, this is the energy unit. You need to think about energy. And so you solve the problems with energy. Or this is a kinematics problem. You should be thinking about kinematics. But in reality, when you do physics, there are no rules that tell you here's a problem. You should approach it with energy, or you should approach it with momentum, or whatever. You have to figure it out what the approach should be yourself. Okay, and so a good rule of thumb is if two objects are colliding, you want to be thinking about momentum, okay? So whenever I see two objects, whenever I'm analyzing a physics scenario and there are things hitting each other, smacking into each other, my brain is automatically thinking, okay, momentum is going to allow me to figure this out, okay? Now, why is that? And the reason why is that there is a law called the law of conservation of momentum. Law of conservation of momentum. So type it into the chat if you remember what is a conservation law. Conservation law is something that has a very specific meaning in physics. Type it into the chat if you know what a conservation law is. And that's different from, for example, in government. In government, a conservation law is, an actual, maybe they're trying to save, I don't know, the forest or something like that. Okay, so yeah, a conservation law in general means that something cannot be created or destroyed. Okay, excellent. So conservation law means that the final amount of something is equal to the initial amount of something. Okay, so conservation of mass means the final amount of mass has to be equal to the initial amount of mass. Conservation of energy means the final amount of the energy needs to be equal to the initial amount of energy. So the law of conservation of momentum says that the total initial momentum has to be equal to the total final momentum. Okay? So we're going to do 3 examples. All right? Utilizing the law of conservation of momentum. all of these problems are going to take place in outer space. Okay, why is that? Because when you're in outer space, there is nothing else to absorb the momentum. So what happens if you, for example, what if you were to fire a gun on Earth? Okay, or fire a rifle on Earth. What happens is the bullet has a forward momentum and you recoil backwards. Okay, but here's the thing, because you are standing on the Earth, it's not just you that absorbs the recoil. It's the Earth itself that also absorbs the recoil. So it's you plus the Earth absorbing the recoil. And so nothing really happens because the Earth is so massive. Okay? But what if you were in outer space and you fired a rifle? Okay? In that case, because you don't have the Earth backing you up, essentially, you would actually start tumbling backwards in response. Okay? So that's the example we're going to do first. This is an example. It's called a recoil velocity problem. Okay? So we have an astronaut in outer space. Okay, the astronaut has a rifle, and the mass of the astronaut plus the rifle is 70 kilograms. And the astronaut is initially at rest. Okay, and then the astronaut fires the rifle. Okay, so the astronaut fires the rifle. Here's the rifle bullet. It's headed this way at 200 meters per second. Okay, and the bullet has a mass of, let's say the mass of the bullet is 0.15 kilograms. Okay, and here is the so astronaut recoils backwards. Okay, so the question is, what is the final velocity of the astronaut after firing this this round? Okay, so we're going to use conservation of momentum. So the initial momentum, notice how momentum is mass times velocity. Mass times velocity. So if the velocity is 0, you have no momentum. So see how everything is at rest initially? So all the velocities are 0, which means the initial momentum is 0. Okay? For the final momentum, we have two pieces. Okay? We have the momentum of the bullet, and we have the momentum of the recoiling astronaut. So the bullet has a mass of 0.15 kilograms, and it has a velocity of 200 meters per second. And I'm going to put it in as positive 200, just to emphasize the fact that momentum has direction. Okay? So that's the momentum of the bullet. The astronaut has a mass of 70, and it has an unknown final velocity. All right? So notice how the final momentum is mv plus mv. You got an mv for each object. Okay? Now, because of the law of conservation of momentum, the momentum before the bullet is fired is equal to the momentum after the bullet is fired. So I set these two equal to each other. 0 equals 0.15 times 200 is 30. Okay, subtract 30 to the other side. Divide both sides by 70. and I get that V final is minus 0.43 meters per second. Okay. All right. So I want to make a couple of observations. The first thing is, that's all right. This guy is not an observation. The first thing is that the recoil velocity is in the opposite direction of the velocity of the bullet. Okay, why is that? That is because if the initial momentum is 0, you have to keep the momentum at 0. So if the bullet is fired forward, the bullet has positive momentum. So the only way you can add to that and get a momentum of 0 is if you have a negative momentum. Okay? So the recoil is always in the opposite direction of the direction that the thing was thrown. Okay? So that's my first observation. The second observation is that the recoil velocity in this case is much smaller than 200 meters per second. Okay? Type it into the chat if you know why the recoil velocity of the astronaut and the rifle is much smaller than the velocity of the bullet. Yo espero. Excellent. Yes, the astronaut has more mass than the bullet. Okay, so whichever thing is more massive is going to have the slower velocity. So because the bullet is much lighter than the astronaut, the astronaut has a smaller recoil velocity than the bullet does. Okay, and this is connecting back to my comment about why do I do these problems in outer space? It's because if you were to do this on Earth, okay, again, I said it's not just you that absorbs the recoil. It's you plus the Earth because you're standing on the Earth. So the amount of mass is not just your mass. It's the mass of you plus the mass of the Earth, which is so huge that the recoil velocity is essentially 0. So you feel the recoil. You feel the force from the recoil. But the reason you don't actually go flying backwards is because it's not just you experiencing the recoil, it's you plus the Earth. Okay. So let's do another example. This example is what is called a completely inelastic collision. A completely inelastic collision. And so a completely inelastic collision means that they collide, two things collide, and they stick together after the collision. Okay, so they don't hit each other and bounce off each other. They collide and stick. All right? So not like pool balls, for example. Pool balls, yeah. So what does it mean to be stuck together? If two things are stuck together, then they have the same velocity. Okay? Why is that? If two things have different velocities, then that means they're going at different rates, and so they would slowly separate from each other. Okay? So, so they have to have the same velocity if they're stuck together. Okay, so here's an example. Suppose we have two astronauts that are drifting towards each other. Okay. This astronaut has a mass of 70 kilograms. Okay. And is headed this way at 11 meters per second. This astronaut has a mass of 40 kilograms and is headed this way at 5 meters per second. So to spice it up a little bit, we'll say that these astronauts are in love. That's why they're going to stick together, because they love each other. All right. Actually, I would say this astronaut is more in love. They're headed that way faster. Okay. There's an asymmetry in the relationship. It's probably not going to work out. All right. So they collide and they stick together. For some astronaut hanky-panky. Okay. And the question is, what is the final velocity of the pair? And after they collide and stick together. And remember, because this is a completely inelastic collision, there is only one velocity because they both have the same final velocity. So let's look at the initial momentum. The initial momentum is going to be the momentum of this astronaut, which is a mass of 70 times a velocity of plus 11 meters per second to the right. And then the momentum of the second astronaut is m, which is 40, times v, which is 5 meters per second to the left, to give, so that's 770 minus 200. So our initial momentum is 570 kilogram meters per second. Okay, the final momentum is going to be the mass of the first astronaut, which is 70, times the velocity of the first astronaut, which is v final, plus the mass of the second astronaut, which is 40, times the velocity of the second astronaut. Notice how I'm using the same velocities because it is a completely inelastic collision, so they collide and stick together. So because those are the same velocities, I can collect like terms. So 70 v final plus 40 v final is 110 v final. Okay. In the future, if we do a completely inelastic collision problem, I will skip this step and I will just go directly to 110 v final. Okay, because I know they have the same final velocities. From the standpoint of momentum, if two things are stuck together, then sort of their identity as two separate things becomes irrelevant. And so it's just like once they're stuck together, it's a single mass with the sum of the two masses. Okay? So the initial momentum is equal to the final momentum. So 570, which was the initial momentum, equals 110 v final. Divide both sides by 110. And I get 5.2 meters per second. V final is plus 5.2 meters per second. All right. So they would be drifting to the right after their collision with that speed. One thing I want to point out about today's quiz is if you get a problem where the velocity is negative to the left, you need to put that negative sign in there, okay? So for example, if you were solving this question on the quiz and you put in 0.43 instead of negative 0.43, you're going to get the answer wrong, okay? So make sure you do that. All right, we'll do one more example here. And this example is about velocity time graphs of collisions. Okay? So a nice way to think about collisions is with velocity time graphs. So let's suppose we have a 3 kilogram object and we have a 2 kilogram object. And each one has a velocity time graph. So here's a velocity time graph, the velocity in meters per second, the time in seconds. This one has a velocity time graph, the velocity in meters per second, the time in seconds. So what does this one's velocity time graph look like? Well, it's going to look something like this. So the velocity starts out at -10, and it's constant. The reason it's constant is because of Newton's first law of motion. Objects in motion stay in motion. So if there's nothing to make the velocity change, it's not going to change. It's just going to stay where it's at. Okay? But then this 3 kilogram object has a collision. Okay? And when a collision occurs, the velocity changes really rapidly. Okay, so maybe the velocity goes like this. So really rapidly, the velocity is all of a sudden going to change during the course of the collision. After the collision is done, the velocity is now constant again. It's just constant at a new value. So the collision rapidly changed the velocity from one value to another value. So maybe it goes from -10 to +4 or something like that. Okay? And the time at which this rapid change occurs is the time at which the collision occurred. So maybe this is 5 seconds or something. All right, so let's now go ahead and look at the velocity of the 2 kilogram object. Maybe the velocity of the 2 kilogram object starts out at +6 meters per second. It's constant. And then the collision occurs. Now, the collision has to occur at 5 seconds because these two are colliding. You can't have one of them collides in the past and the other one collides in the future. Okay, if they're colliding with each other, they collide at the same time. So at 5 seconds, this one's velocity is going to abruptly change. So the question is, what is the final velocity of this 2 kilogram object after the collision? Okay. Now here's the thing. The collision occurs at 5 seconds. So anything before 5 seconds, anything to the left of 5 seconds is before the collision occurred. So this is all before the collision occurred. There's a question, is it 4 meters per second? This one is not an elastic collision, so they do not stick together. So they go like that. So they will not have the same velocity afterwards. Anything beyond 5 seconds, so to the right of 5 seconds, is after the collision. So this is after. All right. So we can use this to figure out what is the initial momentum. So the initial momentum is going to be the momentum of this one. So 3, the mass is 3. The initial velocity, the velocity before the collision, was -10. So 3 times -10 is the momentum of this one. Then we have the momentum of the 2 kilogram one before the collision. So 2 times the velocity of the 2 kilogram one before the collision is positive 6. Okay, so that means that my initial momentum is negative 30 plus 12, negative 18 kilogram meters per second. All right, the final momentum is everything to the right of 5 seconds. Okay, so for the 3 kilogram object, I can see that after the collision it has a velocity of plus 4. So 3 times plus 4, positive 4 is the final momentum of this object. For this object, the final momentum is 2, which is its mass, times v final. Its final velocity is unknown, so I leave it as an expression. Okay, so this is 12 plus 2v final. All right, because momentum is conserved, I can set these two equal to each other. So I have negative 18 equals 12 plus 2v final. Subtract 12, negative 30 equals 2v final. Divide by 2, and I get negative 15 meters per second is v final for the 2 kilogram object. So basically negative 15 is maybe like down here. So here's negative 15. So this velocity is going to really rapidly go like that. Okay. So that's how this works. Okay, so that is my my lesson for today. I don't think I forgot anything, so I will stop there and I'll see you in the Zoom room.